So this is a short video just to go through G part I from question 2 of the paper 3 mock. It was not an easy question at all. Those 4 marks are very challenging. It's nice that it was a show that question though, because it meant that if you couldn't do G part I, you could still do Euler's method in G part II, and those should seem like hopefully fairly secure marks, those last 3. So what's going on with G part I? We're looking at finding an expression for dH by dt. This is capital H now, and capital H is the height of water in the lowest container. So obviously water is going to come in from the higher container, but it's also going to leave the lower container, and the rates that will happen will vary. And that's what this whole question has been about, this idea of the rate changing. So we need to set up this equation. We actually need to think about the dH by dt is going to be made up from the rate water is entering from top minus the rate that the water is leaving the bottom container. Rate water leaving bottom container. Okay. So there's 2 parts to it, aren't there? So let's just think about the first part. The rate the water is entering from the top. The rate the water is entering from the top is the same as the rate it's exiting that top container. It's just one is positive and one is negative. Now, part D and E were all about this container filled up to a height of 3.2, which is exactly what we've got here. It's filled to 3.2. So we came up with a particular solution for the height of that container, the height of the water in parts D and E. We also found the value, the constant C, and we were given R, which is just the radius of the valve. So we have this expression for H. So we could find an expression for dH by dt, which is the rate that the water is exiting the upper container. And we're going to have to do some chain rule here. T is our variable, C and R are parameters that we know. So doing the chain rule, the inside function is this C minus R squared T. The outside function is 17,640 x squared. So the squaring, we're going to multiply by 2, which is, 35,280, I believe. We're going to reduce the power by 1, so that's down to a power of 1, and we're going to multiply by the derivative of the inside, which is negative R squared. Okay, we can substitute in C's and R's. They're quite messy numbers, which is unfortunate, but we can do that. So I'm going to need a calculator now. So I want 17,640. Let's just make sure that's right. 640 times 2. Then we want to times it by negative R squared. So negative times negative 0.023 squared. 0.023. Okay, so that's the first number I want. Negative 18.66312. And then I'm going to put in C minus R squared T. Okay, so that is the rate that the water is leaving the top container and the rate that it's entering the bottom container. It will be positive when it is entering the bottom container. So d big H by dt now. This is the lower container is going to be the positive version of that. Oops. Oh dear. Sorry. 6312 times 0.013468 minus 0.023 squared t. Okay, we then have to take off the rate that it's leaving the bottom container, and from that I'm going back to part D. This is the rate it's leaving our container. The only adjustment we need to make is H, big H, is the height in this question. So I'm just going to change that lowercase h to a uppercase h, so minus r squared. Oh, we know r. 0.023 squared, square root 70650h. Okay, and then we need to try and make it look like the actual question. So if we look at the question, we've got a constant term, a term with t, this is our constant, and a term with this square root capital H in it. So we need to do the same. We need to, well, I guess this, when we distribute, will be our constant. This is going to be our t term, and hopefully this is our, oops, I said capital H. This is our capital H term. So it's just a case of doing some multiplication now, expanding it all and simplifying.